Okay. Good morning, all of you. First of all, happy Engineers Day to all of you. You are going to be next pillars of this society. So don't take that also very casually. Literally, you are going to build the next machines, and you are going to be part of various companies that contribute to the growth of our country. Okay. So happy Engineers Day, all of you. And today. First I will take the revision of last lecture where we took derivation for the COP of the VRS system. Okay, so welcome to this lecture of refrigeration and air conditioning. And so first of all, I will take the revision of last lecture. So in last lecture, we are seeing thermodynamic model of VRS system. So VRS system stands for vapor absorption refrigeration system, in which the compressor part of VCRS system is being replaced by absorber, pump, and generator. So why we are doing that? So we want to reduce our dependency on electricity. So in case of VRS system, we are not that much dependent on electricity. We are depending on various renewable sources like solar energy or others like a waste heat. So from using that waste heat or solar energy, we are supplying energy to the generator. So in this case, dependency on electricity is minimized. Also, if uh, if you use the compressor, in case of compressor, a lot of noise and vibrations are observed. So that are also omitted in the VRS system. So that is the beauty of VRS system. Next thing in this, before going to our thermodynamic model, actually I showed you what are the heat and work interactions in this system. See here, this diagram is familiar to you. If it is not, I will just give a quick revision. Okay. So this is a VRS system, what you see on the screen. We have evaporator, expansion or condenser, as same as the VCRS system. This compressor part of VCRS system is replaced by this circuit. So this circuit is for absorbent, right? So in VRS system, we have absorbent and absorbent. Absorbent is the substance which absorbs the absorbent. So we have water as an absorber, and absorbent is a refrigerant, that is the ammonia. So herein we have absorber in which the water absorbs the vapor ammonia, which is coming out of evaporator. So strong solution is being formed. It is pumped with the help of pump. Then it is passed to generator. In generator, heat is supplied. Now there is a difference between their boiling point of ammonia and water. Because of that difference, the ammonia is first liberated and then it is passed to condenser. Water, then it will boil and it will pass to the absorber. So that ammonia will pass to the condenser. It will give off its latent heat and it will be converted into liquid. So liquid ammonia will pass through the expansion valve, in which is pressure is reduced. So pressure is reduced means the temperature also subsequently is reduced and then it is passed to evaporator. So objective is evaporator, we have to extract the heat from the low temperature reservoir. So there are two circuits. One circuit is for the absorber. So this circuit is for the absorber, which is water in our case, and this outer circuit is for the refrigerant or the absorbent. In this case, it is ammonia. Okay. So here, first we'll see the heat interaction. So in this case, heat interactions, first is QE. QE is nothing but the heat which is supplied, which is extracted in the evaporator. Next is QA. QA is the heat liberated in the absorber. See that this the phenomena of absorption. It is a exothermic reaction. Endothermic reaction. Heat is being absorbed. So the temperature increases here. So if we want to reduce that temperature, we are using a cooling water in that case. So that is the heat which will be rejected to the cooling water. Next is QG. QG is the heat supplied to the generator. We are using steam or heating coil or solar energy in that case. QC is the heat rejected in the condenser. Okay, so these are the heat interactions. Coming to the work interactions, we have QP. QP is nothing but whatever work we are supplying. QP is the work supplying in the pump. Okay, so these are the heat and work interactions for the VRS system. We have QE, that is the heat is extracted in the evaporator. QA, heat released in the absorber. QG, heat supplied to the generator. QC is the heat released in the condenser. Work interaction, we have QP, that is the work which are supplying to the pump. Okay. From then I will apply the first law of thermodynamics. So if so this is a simplified diagram here. So we have a system, it is a VARS system. Then like I told you previously, heat interactions, we have QE, it is the heat extracted in the evaporator. T is the temperature of the evaporator. Okay. Next is QG. Here QG is the heat supplied in the generator, which is at the temperature TG. Then we have QA, heat release in the absorber. QC, the heat release in the condenser, which is at the temperature TO. So here it is assumed that this temperature of absorber and the condenser, they are same. If it is different, we can consider that also. But for simplicity purpose, we have considered temperature of absorber and temperature of condenser as the same, that is a TO. Now in this case, we know that the sign convention for the heat and whatever heat supplied to the system, that will be positive. Heat supplied by the system or release, that will be negative. So as you see here, these two arrows are pointing towards the system, that is heat supplied. This blue arrow and red arrow, so that will be positive. And heat released by the system, this arrow, orange arrow, so that will be negative. So that QA plus QC will be negative. So always remember, in case of heat, the system of the heat येत असेल तर ते पॉझिटिव्ह आहे, सिस्टम कडून heat जात असेल, so it will be negative. It is like a account statement. जर माझ्याकडे कॅश येत असेल तर ते पॉझिटिव्ह झाली आणि कॅश जर मी देत असेल तर ते निगेटिव्ह झाली. And opposite is in the case of work. तेच ऑपोजिट आहे वर्क मध्ये. If work is supplied on the system, that will be negative. If it is work done by the system, that will be positive. So I think all of you know this sign convention. So according to first law, I will apply the first law. In first law, we have work and heat interactions. So you know that for a cyclic processes, cyclic integration of heat is equal to cyclic integration of work. So if I go for processes, I have that equation Q is equal to U plus W, where U stands for internal heat. Now in this case, I have considered we are a system as a whole. So all temperatures will remain constant. So temperature being remaining constant, that internal energy, there will be no difference. So that will be 0. So in this case, as you see here, QG is positive, QE is positive because the heat is supplied to the system, minus QA plus Q condenser. So that is a heat supplied by the system. So that will be negative, minus QP, that is a work done on the system. Okay, so this QA and condenser heat is replaced by QC. So neglecting pump work and assuming QA is equal to QC is equal to Q, so that condenser, all this heat is I have replaced by QC. Okay. Next is QG plus QE, so minus QC. So this will be the simplified equation, or in simple words, I can write it as a QC is equal to QG plus QE. Okay. By simply just applying first law, I have derived this equation. Okay. Then I have applied the concept of entropy. So in entropy, we have Clausius statement, Clausius inequality. So all of you know that Clausius inequality, if I consider for cyclic processes, okay. In case of cyclic processes, I have this dq by t less than equal to 0. If I go for processes, in that case, ds or change in entropy of the system is always greater than or equal to dq by t. So in that case, I will apply this for the cyclic process. So I will apply this dq by t is equal to 0. So dq by t, nothing but a change in heat divided by the temperature. So in this case, Qg is supplied at the temperature of Tg, which is positive, plus Qe divided by Te. Okay, this is also positive, minus Qc by To. Qc is supplied at the temperature of To is equal to 0. This is simply, I have applied the Clausius statement for a reversible processes. So in this case, I have assumed that all the processes in the system are reversible. So assuming that, I can apply the equation dq by t equal to 0 according to Clausius inequality. Okay. So all of you remember that entropy chapter. So entropy is nothing but degree of randomness and entropy of generation. So entropy always increases in the universe because all the processes practically they are irreversible. Okay. Irreversible case मध्ये equation काय असतं आपलं, the ds is equal to integration dq by t plus entropy of generation. So the entropy generation नेहमी काय असतं, greater than or equal to 0. Entropy of generation is 0 for only reversible processes. And entropy entropy of generation is always greater than 0 in case of irreversible processes. So that is why that statement you might remember that entropy always in the universe always increases. Okay. So I have simplified this equation. Okay. So as you can see on the screen, this QC I have replaced by QG plus QE from where? From this equation. So QC I have replaced by QG plus QE. Okay. So what I will do from this step onwards, I will take out QG by TO to the LHS and I will take this QV by TA to the RHS. So that you can see in the next step here. So QG by TG minus QG by TO is equal to QE by TO minus QE by TE. In this case, there's QG, I will take the common. Here I have taken common. QG in bracket 1 by TG minus 1 by TO. Similarly, on RHS. Now, after this step, why I'm doing this derivation? To calculate the COP. COP, as you all know, COP, that is a coefficient of performance. So for a VRS system, what is our objective in a refrigerator system? To extract the heat. So heat is extracted, that will be our objective, that is nothing but QE divided by the input. त्यास तुम्ही efficiency काढता, COP काढता, लॉजिक सेमच आहे. न्यूमरेटर मध्ये तुमचं ऑब्जेक्टिव्ह असतं, डिनॉमिनेटर मध्ये तुमचं इनपुट असतं. तर तुमचं न्यूमरेटर मध्ये ऑब्जेक्टिव्ह काय आहे? टू एक्सट्रॅक्ट द हीट, दॅट इज अ QE. डिनॉमिनेटर मध्ये काय असणार तुमचं इनपुट. सो व्हॉट इज युअर इनपुट इन दिस केस? दॅट इज अ QG, heat supplied to the generator. So you can see at these two equations, COP is QE divided by QG. So you can do the same in the above equation. So I will take on one side QE by QG and remaining this term I will put to the LHS, right? So divide equation 4 by equation by QG, right? So this is how you will get. So in last lecture I have taken this derivation. If anybody was absent in last lecture, you can just follow with me and you can write the last equation of COP. So there was some rearrangement of terms. Okay. So on one side I have taken QE by QG, that is nothing but COP. On another side I have taken all these temperature terms. So QE by QG, this will become like this. So finally the equation I will get it as a COP. So why it will be max? Because I have assumed all the processes are reversible. So if a engine or a refrigerator which has a reversible process, that will give you maximum coefficient of performance. So that equation is here COP max is equal to TG minus TO divided by TG in one bracket and into another bracket TE divided by TO minus TE. Okay. Now you see this equation carefully. Okay. So here if you see TE divided by TO minus TE. So this reminds me efficiency of sum. Okay. ही efficiency कशाची असते? ज्यावेळेस तुम्ही Carnot heat engine कन्सिडर करता. इफ यू कन्सिडर Carnot heat engine ची efficiency काय असते? 1 minus TL by TH. So TL is low temperature reservoir, TH is high temperature reservoir. Similar equation I have obtained here, TE divided by TO minus TE. Okay, and here in this case I have TG minus TO. Okay, so this is a Carnot engine efficiency. This is a refrigerator efficiency. So simply I will put a diagram in front of you, and then you will come to know. Okay, so you consider these two equations. Okay, so we can simplify this derivation into this diagram. Okay, so we can assume that there are three temperatures we are dealing with. First is the TG, which is the highest temperature. In middle temperature we have TO, and the lowest temperature we have a TE. Okay. Now watch closely. Here in this equation, so we have TG minus TO by TJ. So this gives you idea about the efficiency of a Carnot engine. तुम्ही जर efficiency of Carnot engine बघितले असेल ते काय असते? Work done divided by QH. So that is nothing but 1 minus TL by TH, right? Or we can say TH minus TL divided by TH. So in this case, we have TG, which is a TH, which is a higher temperature reservoir, minus TO, which is a lower temperature reservoir, divided by TJ. So this is nothing but the efficiency of a Carnot engine. Okay. So similarly, here in this diagram, you can see here we have TG, we have TO, In between, I have a Carnot heat engine. So it will take a QG from the high temperature reservoir. It will do some amount of work and it will release some energy, that is a QA. So you are very familiar with the Carnot heat engines. They operate between the high temperature, low temperature. मध्ये एक Carnot engine असतं, it will take the heat, it will do some work and it will release some heat. So we can say that that term belongs to Carnot heat engine. Now coming to the next term here, that is a TE divided by TO minus TE. So this is for the Carnot refrigerator. Okay. How is it? I will show you. So next thing here, it is a TO and TE. So there is a Carnot refrigerator which operates between the TE and TO. It will take the heat QE from the TE and it will require some work for it and it will release the heat of QC. Okay. So efficiency in this case will be what? So that will be TE divided by TO minus TE. Okay. So we are dealing with two Carnot, what you can say, machines. So first is a Carnot heat engine, another is a Carnot refrigerator. And what equation I have obtained here, COP of a VRS system is equal to efficiency or the Carnot efficiency of heat engine into Carnot COP of a refrigerator. So you can write somewhere here that COP of VRS is equal to efficiency of Carnot into COP of a Carnot refrigerator. Okay, so this derivation is very important. It asked in the university examinations. So for this derive this equation for the maximum COP of a VRS system. So keep in your mind that ज्यावेळेस तुम्हाला म्हणतात की COP of VRS system, it is just a product of Carnot engine's efficiency into Carnot refrigerators COP. Okay. So draw this diagram and write that equation. So we'll come to know what we are dealing here with. Okay, so I hope you have drawn this diagram. Also for a reference, you write this equation also for the COP because I'm going to take a numerical in which you will require this formula. Right? So write down this equation for the COP max also.
Hello, sir.
Yes. Yes, Arbaz.
चव्हाण सरांनी लिंक टाकली 11 वाजता लेक्चरची.
I will tell him to take at 11:30. Okay. Okay, so I will put the example in front of you, and meanwhile I will call the answer. Okay. So example is in front of you, and this is a one-step answer you will get if you apply that formula. Okay, so example is in front of you. In a VRS, vapor absorption refrigeration system, heating, cooling, and refrigeration takes place at a temperature of 100 degrees Celsius, 20 degrees Celsius, and minus 5 degrees Celsius respectively. Find the maximum COP of the system. Okay, so just now we have written the formula of the COP max, that is equal to. Okay. So apply that formula and you will get the answer. So first of all, you tell me. So in COP, we have formula as TG minus TO divided by TG into TE divided by TO minus TE. Okay. In this step or in this example, tell me what will be the TG? What will be the values of TG, TO, and TE? Okay. So you can put in chat box what will be the value of TG, TO, and TE. Okay, so I have one answer here given by Dayanand. Yes, so TG is equal to 100 degrees Celsius. Yes, so heating. So in generator, we are heating the strong solution. So that is why its temperature will be 100 degrees Celsius. Then TO is 20 degrees Celsius. Yes, cooling. So cooling means in condenser cooling. So that is why its temperature is 20 degrees Celsius. Refrigeration means obviously we are using evaporator. So that evaporator temperature TE will be minus 5 degrees Celsius. So calculate that COP and tell me the answer. Okay, in one step you will get the answer. Yes, so what will be the answer? This should not take that much time. You know the formula. COB max is equal to Tg minus To divided by Tg into Te divided by To minus Te. So just put the values there, but make sure you put it in Kelvin. Okay, don't put in a degree Celsius. Yes. What is the answer? Why it is taking that much time? Shall I show you the formula once again? This is the formula. Here in this case, Tg's value is given 100 degrees Celsius. To that is given as 20 degrees Celsius. T is given as minus 5 degree Celsius. Okay. Just put the values there and put it in Kelvin. So you will get the answer. So you put your answers in chat box. This should not take that. Arbaz, please calculate and tell me the answer. Arbaz, please calculate and tell me the answer. I have one answer in front of me. Others, please also calculate so that I can verify it. Okay, I have only one answer. Others, please also calculate. 0.16 is a very low COP, so this should not be the answer. Akshay, please calculate once again. Okay, so in this example, already the values are given. TG value is given 100 degrees Celsius. TO is given as 20 degrees Celsius. T is given as minus 5 degrees Celsius. Okay, so put the values in the equation and you will get the COP. 1.72. So have you converted into Kelvin? It is converted into Kelvin and then calculate. So 100 means that will be 373. 20 degrees Celsius, that means that will be 293. Minus 5 degrees Celsius, that means that will be 268 Kelvin. So one more answer I have here, 2.29, which looks good. Others, RBAS calculate once again. And remember to convert it into Kelvin. So temperature that you should convert into Kelvin. Okay, one more answer I have here from Rohit, 2.2991. Right. So 2.29 or in general I take 2.3 is the correct answer. Right. So for the given VRS system, maximum COP will be 2.3. So maximum COP means we are assuming that all the processes in this system are reversible, which is not practically possible because there will be irreversibility in the system in case of pressure drop or friction. Because of that, the COP will be less. Practical COP will be lesser than this one, but the maximum COP what we can get from it here, it is a 2.3. Okay. This is about the derivation and the simple numerical I have taken. Actually, they are not asking numericals in the examination, but still for clarity of this derivation or the formula, I have taken this numerical. Right. Okay. Moving on. So up to this point, we have seen only one solution in this VRS system. Okay, Akshay, thank you. You have calculated correctly because you have calculated very less value at the starting, 0.16. Okay. So take care in future. You convert that temperatures from degree Celsius to degree Kelvin, right? Okay. So moving on. Up to this point, we have taken only one solution, that is aqua ammonia. Water and ammonia solution we have only considered. But apart from this, there are other solutions also which are used in the market. What are those? We'll see. So there is a table in front of you, and we first column here it is the refrigerant. Second is absorber. Refrigerant will be absorbate, and we have a absorber. Then there is a state of absorber. Okay. So first we have already studied, that is ammonia. Ammonia acts as a refrigerant. Water. So why we are taken ammonia and with water? Because water has very great absorption capability for the ammonia or affinity towards the ammonia. So I showed you that video of ammonia fountain. In that case, what happens? Ammonia gas has been absorbed by the water. It creates a pressure drop. In order to compensate that pressure drop, water is being forced through a tube, and that creates a water fountain or ammonia fountain. Okay, so we have ammonia and water. State of water here, it is liquid. Second is ammonia and sodium thiocyanate. So that is thiocyanate is in solid state. Third, we have ammonia and lithium nitrate. In that case, lithium nitrate is in solid state. Fourth is ammonia and calcium chloride. In that, calcium chloride is in solid state. Again, we have ammonia as refrigerant. So you can see here 5 times ammonia has been repeated because ammonia has very good refrigeration capacity. Okay, so it has, though it is very toxic, but if you consider refrigeration system, they prefer ammonia. If this ammonia and isobutane, so in that case, isobutane is also in solid state. Isobutane, as you know, that is a gas actually, what we use for burning purposes. But if you compress it to a large pressure and then cool it, so that will form as a solid. Sixth, we have water. So in this case, now here water was absorber. Okay, now we have water as a refrigerant. So water as a refrigerant and absorber here it is a lithium bromide. So we have a lithium bromide system which we'll study in next lecture. State of absorber in that is a solid. Again we have our water and we have lithium chloride. In that case lithium chloride is in solid state. So this chloride means that will be, there will be chlorine. Then the chlorine is very dangerous to ozone layer. So care is being taken not to use the chloride based solutions. Eighth and last is here is methyl chloride. Methyl chloride is the refrigerant and the absorber we have dimethyl ether of tetra ethylene glycol. In that case, state of this absorber it is in liquid state. So in the syllabus we are going to study only two solutions. First it is aqua ammonia and second it is a water lithium bromide. So we have a lithium bromide system that we'll study in next lecture. So in this lecture, we'll see practical VARS system, what are the components of it, okay. So next point in front of you, that is a practical absorber refrigeration cycle. So what we have seen previously, that was a simple or ideal VRS, in which that compressor is being replaced by absorber, generator and pump. But practically we have to assemble or we have to install other accessories also. Which are those we'll see today. So first one is in that case it is a heat exchanger which is installed between generator and absorber. Then we have here analyzer to separate out the ammonia vapors. Then we have rectifier, again same purpose, to separate out the ammonia vapors. Then these ammonia vapors are passed to the condenser, then the cycle will repeat. Okay. So we'll see what are those components. The replacement of the compressor by the simple arrangement is not very economical in practice. So we have seen that COP of VRS will less compared to VCRS in that comparison chart. In order to make improvements, certain additional auxiliary items are provided in the system. They include analyzer, a rectifier, and two heat exchangers. Okay, so we have two heat exchangers. Though in this diagram, only one heat exchanger is being shown. Another heat exchanger, it is installed before the evaporator. Okay, so first we'll see analyzer. So see here, analyzer is installed between rectifier and the generator. So analyzer is nothing but some plates are put in vertical manner. Vertical manner मध्ये plates असतात, त्याला holes असतात. जसं आपण पाणी झिरपतो तसं त्या प्लेट्स मधून ते स्ट्रॉंग सोल्युशन जे असतं aqua अमोनियाचं त्यातून झिरपतं, त्यातून मग वॉटर सेपरेट केलं जातं आणि अमोनिया सेपरेट केलं जातं. So we'll see. Analyzer is an open cooler and is an integral part of the generator. It is a vertical tower with baffle plates to provide a zigzag path and analyzes the vapor and removes any water associated with ammonia vapor coming from the generator. So see here, the objective of the generator here, what happens because of difference in boiling points. What happens first, ammonia is liberated or it is separated from the strong solution and then water is being sent to the absorber. But what happens in this ammonia vapor also, some water droplets will be there. Okay, so we want to remove that water droplets. So what is happening here? This so these vapors are passed to these plates. These plates are managed in the zigzag manner. So they are placed in zigzag manner. And then what happens? These water particles, when they come contact with the surfaces, they adhere to it. They get attached to these surfaces and thus they are removed. So we get ammonia vapors at the outlet. That is a function of analyzer. It removes any water associated with ammonia vapor coming from the generator. Okay. Next is rectifier. So we'll see what is rectifier. Then dry vapors. Then dry vapors means whatever vapors coming from the analyzer. Then dry vapors will be sent to the condenser through the rectifier. Rectifier is a closed cooler. In this, ammonia vapors are indirectly cooled by water. Any small traces of water associated are removed by the rectifier. See here rectifier, you can see here in this diagram, it is nothing but a heat exchanger in which we have a water tubes. So water coming in and water is going out. So water will take the heat from this ammonia vapors. So if vapor is containing any water particles, so that will be condensed, and that condensed water will be sent to the analyzer. So you can see there is a drip line which is connecting a rectifier and analyzer. So what is happening in rectifier? Ammonia vapors. So heat is being taken by the water. Then water particles in the ammonia vapor that will be condensed inside the rectifier. This condensed water will be taken to the analyzer. Okay. So whole objective of analyzer and rectifier is same, to separate out the water particles from the ammonia vapors. And third, we have aqua heat exchanger. So aqua heat exchanger heats the strong aqua going to the generator and thus reduces the heating requirements in the generator. So generator, we know that we supply the heat to separate out water and ammonia. So in that case, it would be better that solution coming to the generator is preheated. So objective of aqua heat exchanger is to preheat the solution. This heat exchanger also cools the weak aqua going to the absorber and thus reduces the cooling requirement in the absorber. Okay, so what it is saying actually, the objective of generator is to heat the solution. So whatever solution coming, so this 4 to 5, whatever coming here, that should be preheated, and whatever solution going to the absorber, that should be pre-cooled. So what you see here, 6 to 7 is pre-cooling. This preheating and pre-cooling, it is achieved with the help of a heat exchanger. Okay. आपण इथं बघतोय की absorber मध्ये आपल्याला सेपरेट एक वॉटर कूलिंग अरेंजमेंट द्यावी लागते टू इन ऑर्डर टू मेंटेन द टेम्परेचर. So that temperature, so in heat exchanger, what is happening? This will give off its heat to this solution. So this will be preheated and this will be pre-cooled. Thus, it is greatly improves the economy of the system. Okay, so we have three auxiliaries, which is analyzer, second is rectifier, and third is aqua heat exchanger. So I'll give you some time to draw this diagram. Please draw it in a very simple way. Block diagram you can draw here. So these components are same from previous diagram, that is absorber, then there is a pump, there is a generator, then we have condenser, then we have the receiver, expansion wall, evaporator. All these components are same. Auxiliaries are here, aqua heat exchanger, second is analyzer, and third here it is a rectifier. So I'll give some 5 minutes, you can draw it. So you should draw a freehand diagram, no need to go for scale and okay. Okay, so I hope you completed drawing this diagram. So practical absorption refrigeration cycle, I will repeat again. So in this case, we are using three auxiliary extras. So that is a aqua heat exchanger, analyzer, and rectifier. The objective of analyzer and rectifier is being same. That is to remove the water particles. Aqua heat exchangers is objective is to preheat the strong solution and pre-cool the weak solution. So in simple words, that will be the explanation. Okay. So that's it for today. Today we have taken this. We have repeated this. I have taken the revision for this derivation of COP max. We have solved one numerical. Then we have seen various solutions of absorber and absorbate. Then lastly, we have seen the practical vapor absorption refrigeration system. Okay. So once again, I will wish you very happy Engineers Day. And whether you do job in MNC, do government job, you do your own business, in each way you are going to contribute to the growth of our country. So our objective or our responsibility is to provide good engineers to the society. Your responsibility is to give value to the society. Okay. So I wish you all the best. And on that note, we'll conclude today's lecture. So quickly, I will take the attendance and then we can stop. Okay. Okay, so I have taken your attendance. Thank you for attending. See you in next lecture.